Well, hello everyone, and welcome to another video from the Canal Sidings Model Railway channel. Yes, it has been a long time. Today is Tuesday the 2nd of March 2021. My last video was on, I don't know what day it was, but the 5th of October 2020. So that is almost 5 months. But I did allude in that video to the probability that I wouldn't be back for some time, because I'd just really only broken the surface of the massive wiring job that I had to do in order to put all the bus wiring around the layout in order to have the possibility of getting trains running again. I have now finished the DCC and power bus wiring all the way round. Some of it is, as you saw in the last video, hanging from the underside of the shelf that holds up the railway, and some of it is actually now through the boards that are conventionally built. For those who don't remember, the board that you're looking at now is actually built from styrofoam with just a wooden wrapping around the outside and cork on the top. None of the track that you see in front of you, or indeed most of on the new section, was laid in October. I've had to lay all of that as well as doing all the wiring, and I have had to wire up each board, which turned out to be a longer job than expected, mainly because the way the styrofoam boards are wired is that there is a large piece of styrofoam taken out on the underside, and I'll show you a bit of that when I can. A large piece of styrofoam is taken out from the underside, and a piece of 4mm MDF is glued in place, and all the electronics is then screwed to that. What I decided was, for the board you're looking at now and the one that is just that way of it, there's a lot of electronics on it, because there are 2 Arduinos on each board, one in each case operating points and the other operating signals, which required a lot of wiring up. And I decided to actually make the MDF board and all of the electronics an assembly, and then glue the board underneath the layout. That meant that during the cold weather of what turned out to be a bit of December, all of January and pretty much most of February, I was able to sit in the warmth of the lounge and do my wiring up. So I managed to get quite a lot of it done. And so there's part of the reason why it's taken longer than expected. Also, my old mother died, 96-year-old mother died on the 12th of January, which did slow me down a bit. We were prepared for it, because she'd been drifting away for the past couple of months, and we didn't expect her to last very long. But I do have to say, it hit me harder than expected, and it did slow me right down for a couple of weeks. But I got back into it, and then, and I'm still in this now, I had a bit of a health scare. So far everything that they've tested is fine, and there's a couple more things that they're about to do, and hopefully that'll all be fine and I can go back to normal. So that slowed me down a bit anyway. The other thing that slowed me down, and I shall pick the camera up now and walk along to the other end of the layout and show you what I'm about to talk about. Okay, we're down the other end of the layout now, and I'm hand holding the camera, so apologies for the shake. But this board here, which starts there and actually finishes here, that board has got a Hornby set track on it. The 2 outer tracks are 4th radius and the inner one is 3rd radius. And initially the baseboard joints, and I'll just take you along to the previous baseboard joint. Oh, I haven't got a long enough wire on my camera. My battery's gone flat, so I've had to, I'll just zoom you in. There is my baseboard joints as they were, which are copper clad sleepers. I'm not sure all the copper clad is in there actually. I think one end's missing, not been put in yet, but they're copper clad sleepers pinned down to inserted pieces of MDF, and then the rail end soldered to them. Now on that one and the one all the way down there, which doesn't seem to want to focus. Camera's not seeming to focus very well, unless it's my eyesight. Oh, that's better. There's one right down there just under that train, and one just behind it. All those baseboard joints were fine. However, the baseboard joints that were there, that's the one that is here, here and here, I could not get trains to run over them reliably. I have no dowels between these because they need to slide in and out, so I can't put baseboard dowels in. So I have a real problem over there in that, I had a real problem over there in that I could never get those three joints to align, and usually all three were bad, and I just got constant derailments. Also the ones at this end, which is along this line, also weren't particularly good. That's leading up to the bridge section, but at least I could get them to align, but not that end. So what I decided to try and do, that's my hand in front of the camera, sorry about that. What I decided to try and do was come up with another method of mounting the track. And my first idea, and I'm just going to put the camera down and go and get a piece of track to demonstrate what I'm talking about. So I'll just drop that there for a minute. Sorry, I haven't got a long enough wire on it. As I say, battery's flat, and I'm having to run it off of its charger. And good old Panasonic only provided about a metre of cable. Anyway, here is a piece of track that I experimented with. Sorry, finger in the way of the camera again. I'll just put it on. Yeah, shaky, but not very professional. But what this is, it's a piece of pre-ballasted track. It's a bit of Hornby track. It happens to be first radius, I think, this one. And what it's laid on is a bit of cellophane. Simple as that. And it's laid on there. The cellophane is glued. The back of the track is glued. The track's dropped into the cellophane. And then ballast is dropped in. And the whole thing's left to dry. And I wondered whether I could do that and just lay the track on top of the baseboard. There's too many pins there, like that. And then connect it with rail joiners at both ends. That was actually better than I thought, although by the time it had dried, I decided that I had a better idea. The idea was that I would have rail joiners on both ends, and I would push one end in and then push the other end in, and that would make the electrical connection as well. So the track wouldn't be fixed down around those corners. But what I realised was that this piece of track was never going to work like that, because there's not enough wiggle room to get it to twist and go into the space. The one over the back there probably would have been alright, and the next one would probably have been alright. But what I eventually did was I left these tracks fitted to the cork, and I've actually cut the cork along the edges of the track and lifted the cork up. So now the assemblies are, each one of those tracks has its piece of cork under it, and I can lift them out. This end I use sliding rail joiners, so I just slide them back that way. This end of the track will lift, and then round this end I've got soldered on rail joiners, soldered to this piece, and this piece. God, it's hard to hold the camera and reach across as well. And they just pull out, and they come with their piece of cork, and underneath you see a gap between the cork down to the styrofoam. I wasn't expecting problems like that, but there you go. I'm sure that the alignment problems were more down to the fact that these are quite sharp curves here, and unless you align them absolutely perfectly, they just don't work. But I've got a system that will work. I've thought about all of the problems of doing scenery on the board. There's not much scenery, and mostly here it's going to be trees to hide it. There's going to be trees at the back to hide that bit of back scene, and then I shall just in the middle just put virtually nothing. There will be overhead running round, and they will have to be removable, but I'm not putting wires on the overhead equipment, so the masts will come out easily enough, I hope. I'm thinking of trying to use magnetic fixings for overhead masts. Just what are they called? Neodymium magnets glued onto the bottom, and then when you drop the mast into the hole, the magnet gets a grip and the mast stays upright. That's what I'm thinking about. Don't know if I've got a chance of doing it, but we'll see. So that's another thing that slowed me right down. I must have spent half a week's modelling time trying to get that to work. What I've also done during the time is, I'm going to get back down here now, you can see this bridge has now got a front fascia board on it, and it has also got a rear fascia board. I've also got a place just here to make the connections, and this is actually typical of how all the baseboards are connected. They're connected via these D connectors. This happens to be a 15-way. There is also a 25-way, which is down here, not wired yet, which plugs into that one up there. He said trying to do it left-handed. There you go. I'll try to plug this one back in case I start the trains again, because they ain't going to run very well without it. Okay, so that carries the power bus into this board, and powers all the tracks, and gives me the 5 volts for the signalling and 12 volts for any accessories that happen to be on there. So that's something else that I did. I've got this piece of wood in now, which is going to be turned into the riverbed, which I intend to use PVA. Kathy Millett showed a method of using PVA to make water, and it looked a very economical method. Some of the realistic waters that you get are terribly expensive. So that's what I've been doing there. I'm going to have to pull the camera plug out now, which is probably going to mean I've got no power, but we'll see if I can get back down the other end of the room. Oh, well, first of all, I'll turn around this way. You'll have to excuse the mess in here, but it really isn't very tidy. You saw that board before. I had done most of that one, although I have now, I'll just zoom in a bit, it finishes just there and runs through to just the end of the bridge there, and that is all wired through. If you look under the bridge section here, you can see the wiring that is part of the bus system, and that, as you saw in the last video, runs all the way under there and runs along the back up there. This layout doesn't belong here, but it's somewhere to put it, and it runs underneath there, fixed to the underside of the shelf. And just over there, falling off the wall because I've not fitted it very well, is one of the relays that switches the braking sections. That was the one that I said, so I've just come out from under there, I don't know what I'm pointing at. That was the one that I said I didn't like in the last video because I'd wired it directly, I'd hardwired to it, rather than the last two. One of them is up under there somewhere, and the other one is, if I don't strangle myself, is up under that board up the end there. I actually put a 15-way D connector on each one of the relay boxes, and now I plugged them in, and the one up the end of the room that I showed you last was faulty. There was a faulty relay in it. Sorry, not there's a faulty relay board in it. It had 2 pins on a jumper wire that weren't soldered. Don't know how it ever got tested, but anyway, that's fixed now. The next board, I'm going to have to turn around this way to it because I'm running out of space and I'm falling over things as well. Okay, that board there, which goes from, oh, where's my finger, there to about there, which you've seen before. That's the one I added some points to some time ago. That board has been wired underneath, and so has that board all the way around the end, and that brings us back to this end here. They've all been hardwired under the board, although there's no signalling buses in, and that is true of the whole rest of the layout. There are no signalling buses in anywhere. So what I'll do next is I'll just take you back down the other end of the room, and we'll look underneath one of the boards, and then I'll show you a photograph rather than hanging upside down of what's under one of the boards. Give you an idea of just how much wiring I've had to do without the backplane, let alone doing the backplane. So I'll just move along again. Okay, this rather precarious shot with me upside down under the baseboard shows you the bit of baseboard that I've had to cut out and inset that piece of MDF to which everything is screwed. And if I get out from under here, which is not easy, and we move up to the top, you can see that it was this baseboard here, that's my power cab, and it was the baseboard that we were looking at. I was sitting on that black pad there with the camera when we first started. And under the next board, which starts here, under here, there's a similar one of those. And what I'll do is I'll now show you a photograph of what I've taken of one of those and just talk you through what the bits and pieces of it are, and then we'll wrap the video up with a little bit more running and I'll try and come back quicker than I did last time, but I've got no guarantees. It depends how much progress I can make that actually shows. So back in a sec. Okay, well, first of all, you'll be pleased to know that I've actually taken the camera and put it back on the tripod, because I won't be shaking it about so much. So what you see here is what is under board 3, which was the one I showed you. Board 3, it says it down here so that we know which board we're talking about. And here we have the two connectors which bring in the power and connect all the signalling system. The small one has all the DCC on it and all of the 12 volts and 5 volts for signalling, etc. And that all goes, in this case, to here, and then the 12 volts and the 5 volts come off here, and the 12 volts goes to this block, and it produces its own 5 volts, and there is also 12 volts that goes to here, I missed it, to here, and the 5 volts for the signalling comes off here. This bit is all about signalling, and so is that bit. This bit is power, and this bit is all about point control. And in previous videos I've showed you what that Arduino essentially consists of, although this is a very much more up-to-date version of anything that I've done a video of before. And this is something that I sort of gave a very quick view of back in an earlier video, which is a DCC decoder and up to 12 servo driver for points, which again I've written all the code in the Arduino for, the same as I have the signalling. And I may go into that further if anybody is interested in it. You can let me know in the comments if you are. And if you're interested in more details on this, I can let you know some more about it. I don't really want to do too many in-depth electronics videos, because I know there are plenty of people out there that don't really want to get involved with electronics, and that's fine. I just happen to enjoy doing this kind of thing. Anyway, we'll go through it bit by bit. I won't go too much. In case you're wondering about these connectors and current carrying capability for power lines and DCC, they are rated at typically 3 amps per connection, 3 amps per pin. Now, nowhere do I take anything like 3 amps per pin. Essentially, I have one power district going in through a pin here, and that power district comes in through here and powers only the board that this is under, which is about a 4-foot long board. That board, which is the one that we were looking at, or the one you saw most of in the running shots, that board is a contains 1, 2, 3, 4, 5 power districts. The 5 power districts are on here. We have a power district, let's look at it here. We have another one here, another one here. They are for the 3 main lines. This one is for the relief, I can tell because it's blue. This one here, can't see the colours. No, can't tell what colours they are, a bit weak. This one's yellow, so it's for the down main. So this one must be for the up main. The colours are easier to see, they're quite bright on the wires normally. And then this one here, which is white and green, comes all the way down here and goes only to there. That's what we call the accessory bus, and I'll talk about that when I come down here. So that's 4 of them, and there is one more which is here. It's green and purple, just here, which is connected to nothing at the moment. None of these are connected because this wasn't wired up at the time. But that is for powering the engineer's yard and loco yard, which will also be on, some of which will also be on this board. And each one of those power districts is current limited at an absolute maximum of 2 amps. So there's no way we're going to put 3 amps through any one of those connectors. Not for any length of time anyway, because we don't want it shorted out for too long. Okay, this connector, we said that one's for the power. This connector here is for all the signals. And as you can see, it only goes into the signalling side. And this one only goes into the power side. So what we'll do is we'll look at point work first. So as I said, this is the accessory bus, and only goes here. It will only go to accessories elsewhere on the layout. It goes to quite a few of them, and it goes to quite a lot of Merg accessory decoders, which are already on the old part of the layout. But what we have here is an Arduino sitting on a breakout board, which can control, with the software in it, can control up to 12 servos from DCC commands. The DCC commands come in via this accessory bus, and this is an interface that takes the high track voltage that spins backwards and forwards between plus 12, minus 12, minus 12, plus 12, and turns it into a 5-volt logic signal here. Have a quick closer look at that. That is that. So it's upside down because I can't get this in. DCC comes in here, and it goes via this LED, which will light when the DCC is on, and via an LED in here, a photo LED, which this is a 6N137. I think it's a 6N137. Hang on, let me just look at that. If I could read it. I think it's a 137. Sorry, I should have been prepared for this. I can read it on here. It's a 6N137 device. The device is a 6N137. Oops, dropped this pointer. And it's an opto-isolator with a logic output. So this side, into those 2 pins, goes the DCC via a resistor. and this diode is backwards across the one in here, so this diode in here flashes at the rate of the DCC signal, and that flashing, i.e. the signal going up and down, is what contains the information. Out of here we get a 5 volt signal, which is there's another LED there so I can see it's happening. There's 5 volts and 0 volt going here to power this, and out of here comes the 5 volt version of the DCC. It's a pretty well known circuit, it's used everywhere. Merg use it in their kits. I've seen it specified by people on the internet from many years ago to anything you want to do to make a DCC accessory decoder. I don't actually bother with reading back through here because I think that's overkill. It's great on a locomotive where you can't get to it, but on an accessory decoder I plug into here, which is the way you program the Arduino, and I've got the Arduino programmed so that I can send commands from the PC here to set up all of the servo values, and that is the way I set up the CVs, if you like, the configuration variables. So I won't go into that any further, but the servos all plug in, 11 of them plug in up to there, and the 12th one plugs in here. Yeah, this drives the pin over there. The yellow wire is the input to the Arduino from this, and the Arduino decodes the DCC signals. You can set its address up to be any accessory address you like, and it will simply set the first servo to that address. Servo number 1 is here, or number 0 if you like, up to 11, or 1 to 12. It sets the first servo to the address you give it, the second servo to that address plus 1, all the way through to this address, to the last servo, which is that address plus 11. So that gives you 12 accessory addresses, and you simply send 1 or a 0 as the command, which sets the accessory one way or the other, which causes it to move the servo. This here is a power supply for all the servos. Now this breakout board, you can buy them, they're about $1.50 each. Normally has 5 volts from the Arduino going all round it. Now just here somewhere underneath there's a convenient place where you can cut that. So the Arduino only uses its own 5 volts, which I get off the 12 volt input here. So the only thing that's powered by the 5 volts via the 12 volts is the Arduino. The rest of the board's 5 volt power comes from here. And this is powered by 12 volts, so this is a buck converter. It converts from 12 volts to whatever voltage you set up on here. I've got it set for 5 volts. Whatever you put in there, you'll get 5 volts out, up to about 30 volts. And that powers the other part of the board via this 5 volt connection here. Now, the reason for that is that servos are very power hungry when they're moving, especially if they're working hard. So this can provide easily enough current for the 12 servos. It's very unlikely that there'll be more than a couple of servos moving at the same time. But even if there are, this can provide 5 volts at 3 amps. This can provide 3 amps out of here. And normally they reckon you need a couple of amps for a servo supply. Unless you've got big heavy duty servos. I use 9G servos. The SG90s, or actually the Hobby King equivalents, are much better. Analog, they're not digital servos. So that's in a nutshell is what that bit of the circuitry is. Oh, there's one thing, I have modified this power supply. These are about £1 each. Buy them on eBay or Amazon. There I've broken a pin which was grounded on this board, because if you look up that device, which is the buck converter controller, you'll find that this pin is known as the shutdown pin, or the enable pin, whichever way around you're looking at it. If you ground it, the output is always enabled, but if you pull it high, then nothing comes out of here. So what I've got this arranged as is when you first power it up, there is no voltage out of here. This pin pulls high. As the power comes up, this pin comes up with it. So no power comes out. So you don't get any nasty twitches on the servos at power up. And then I enable each servo in turn to the centre, to its correct point, having applied the power when I am ready, when I know that everything is pulled up right. So I don't get any servo twitching. Or if I do, it's just it hardly moves the servo. You hear it rather than see the twitch, which is fine by me. And that's why it's there for two reasons. One, to stop the twitching, and secondly, to provide far more power than the Arduino can provide from its 5-volt supply. Right, we'll go on to the next bit. This bit here is all to do with signalling. And so is this. This is the outputs. This board has got a ground signal here. It's got a micro switch here. It's got a sensor here. And it's got an ordinary signal with a feather here. So it's got a bit of everything on it. And this Arduino controls that signal, uses that sensor, and also controls a signal which is on B1, sorry, B2. This is B3, the board next to it, B2. And you can see where that goes because there is actually a red, yellow and green here, which is connected back through here to here and goes off to the other board via the backplane, via the bus, which is not installed yet. But the other board has got the equivalent connections such that it can take that information and drive the signal. This drives two signals. I always use them in the same way. I use them either to control an up and a down signal on two separate tracks that are unidirectional. And signal 1 in my nomenclature in here is always the up signal, and signal 2 is always the down signal. So that can be used like that, or you can program it through here. Again, I can program it with the computer to do different things through here, and you can actually specify that it actually uses a direction signal which goes into one of the pins, which you can use, which you just flick a switch, or you can have anything else driving it. It's any logic signal, it just goes from 0 to +5. And that allows you to run two signals on a track that is bidirectionally signalled. And this runs two signals that face one another. Signal 1 will always be in the up direction, and signal 2 will always be in the down direction, as specified for that track. And they face one another, and the sensor for the signals is in between them. So that whichever way you're running, after you pass the signal, you pass the sensor that says you've passed the signal. And if you're running up, if your current running direction is up, then the down signal is permanently red. And if you're running down, then the up signal is permanently red. And that's the way I've signalled it. And that is mostly, it seems, how signalling works on bidirectional tracks. If they are signalled. There are obviously bidirectional tracks on branch lines that have no signals, or very few, and are operated by tokens, whether they be manual or electronic. But that's another matter, and that's not what I've got here. I've got a main line, which is the relief main line, which can be signalled for either direction. Okay, so this controls two signals, either an up and a down on two different tracks, or an up and a down on a bidirectional track. This here is purely a 5-volt, again, output from my 12 volts up to 3 amps, which is one of the two of these that there are driving all of the signalling. My signalling could take 3 amps if you had just the right conditions. What takes all the current really are the relays. Every time you pick a relay to put the brakes on, you take another 140 milliamps from the 5 volts. So there are 9 relays. At any one time, 6 of them could be on. So that's 6 times 140 milliamps already, which is 6, 4, 24, that's 840 milliamps already. That's a lot of current. The sensors that are connected to here take 40 milliamps each. They're the little things that you've seen before. I don't have one laying around, but they're not on this board. They're bolted next to the track. They take 40 milliamps each. I've got 23 of those in the signalling system, and they are taking 40 milliamps all the time. They don't switch on and off. They're always on. So that's 23 times 40 is a lot more current. Yeah, so I'm pushing 3 amps on my signalling worst case. So what I've done is I've just split it into 2 up to 3 amp drivers. One that will take a worst case of about 1.8 amps and the other one a worst case of about 1.2 amps. So that's why it's here. This is one of them. There is another one not on board B2 but on board B4. It's the next one down. It was the best place to put it to split the signalling bus up. So that's all that is. It won't be on every board. Then the Arduino, as we say, is the signalling controller, and it has 5 volts going into it here. And all I've done underneath on this Arduino is short what would be the V in to VCC. So I mustn't put 12 volts in here. This is now just 5 volts goes in here. And that 5 volts comes from here. It also goes back out to here because it's used for other parts of the signalling system. It doesn't only power this board. And this is what's known as an Arduino Io Expander. Now, in adding all this extra functionality of being able to stop a train in front of a signal by picking a relay. Anyway, as I say, because I've added all this extra, this is an Io Expander. It simply uses the I2C bus that every Arduino has got, and it's plugged in here, to send values to this chip, which is an I2C receiver, and it's got 8 outputs, or 8 pins on it, which can be inputs or outputs. And you send the information, and what this does is it provides you with 8 more I/O pins. So you've got the I/O pins on the Arduino plus 8 more there. I will give you a word of warning if you do ever try to use that on an Arduino. There are 2 versions of this chip. There's the normal version and the A version. They have different base addresses. Each one can have up to 8 different addresses, but there is also a base address, a couple of bits, which mean that you can have 2 of these and have 16 of them in a system. Not that anybody's going to do that for railways, but if you get the A version, and you never know which one you're going to get, it seems, if you get the A version, you've got to change your Arduino to talk to a different group of I2C addresses. That's all I'm going to say about that bit. And as I say, this then has got a lot of I/Os. It drives all sorts of things like that. Some of them go in and out through here, etc. But that's it. I'm not going to talk any more about that because I've already talked more than I intended to, because I do waffle a lot. So I'm going to say goodbye for now. Thanks for watching. I hope this video hasn't got too long. I really have lost track of time. And I will see you in the next video, whenever that is. I will try not to make it too long, and I'm going to leave you with a few more running shots. Bye for now, and thanks for watching.